Move, move, move. Get out of the way. Move. Go sit down.
I've got where I sit it.
I can't help you. I can't help you. 1, 2, 3, 4, 5 on the third row. 1, 2, 3, 4, 5, 3, 3. I'm using it. 1, 2, 3 on the fourth. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. Right there. Love. 65. Serrata and Roberts. Now, I don't usually check roll, but two guys came and handed in their homework and walked out the back door. Oh, that triggers a roll calling every time. That's just wrong. Thank you. I don't know all these cool sayings, but that's a good one. Lane. Oh, I'm sorry. Knutz. Kuntz. Next to G in Dismuke. All right. Okay, we're going to do some truss work again. We're not going to carry it to extremes. By that I mean we're not going to work out a bunch of the equations and everything. We're going to just say what we would do and let it go at that. First, I'm going to make a free body out of it. I've been asked to solve for the forces in GI, HI, and HJ. And you don't have to copy these. You're welcome to copy them down if you want to, but it's not necessary. They'll be posted. The main thing I'd really rather you do than copy them down is to see what's going on. That's the important thing. So I'm going to circle the left-hand end of the structure. I've already solved for the reactions. For no reason, I guess I could just as easily circle the other end. It might even be shorter. I cut the left-hand end of this structure loose, show the reactions, show a force, E, F, G. Somebody's looking for these forces. Too late to get the ones I showed you at first because I've already got a free body here. I give the forces guessed arrowheads and and names. E, G, F, G, F, H. And any members that have been cut, because I don't care about the other ones, and have a slope on them, I'll put the slope on there. The slope of that member is 1.8 by 2.4. So if you would with a calculator, give me a hand, 1.8 squared plus 2.4 squared, take a square root. You happen to have a calculator, I notice. Oh, that's a cell phone. Doesn't it have a calculator in it? What a cheap phone. Even mine has a basic calculator in it. 1.8 squared plus 2.4 squared, take a square root equals 3, right on the money. A little unusual. Thank you. All right. So, and I would call that free body number 2. Because probably I already used free body number 1 to solve for the reactions up there at the top. All right. Mr. Mock, I am looking for the force in Edward George. Who do I like?
Who do you like?
Yes.
Well, you don't like F and G.
Well, okay, I hate F and G, and I hate
That guy too.
F and H, that guy too. So who do I like? I like
You like
EG. That's very good. And since I hate these two people, I follow them until they meet at a point, and I sum moments about that point. So I'm going to say 2 solve. Thank you. This is not going to be pretty all day today. To solve for EG, equation 5. I don't know how many equations I had before this, but evidently I'm on the 5th one. I will sum moments about F equals 0. I'll do a couple, just for the heck of it. Otherwise, we'd have to go home early. But you know how to do this. You better know how to do this. Sum moments about F is equal to 0 is equal to. There's an EG force. He has a 1.8 meter moment arm. Were he to get away from me, he would tend to roll this way about the point I'm summing moments. That's not the way my right hand is made. I would have called that a minus. Your sign convention is your business as long as you are consistent. Next, I see FG, but it goes through point F. I see FH, but it goes through point F. I see the 12, but it goes through F. So here's the 9 kip load is the only other person hanging out. I write down the load without a sign. I write down its moment arm, 2 times 2.4 meters per panel. 2 times 2.4 meters. And then only I find a sign, and the sign says it goes this way were it to get away from me. That's a negative sign. And then I solve for EG. EG is equal to a minus 9 times 2 times 2.4 divided by 1.8. The units are kip meter. Well, that's interesting. That must be 9 kilonewtons. Kilonewtons. Meters cancels meters across. And then I'm left with kilonewtons. And that says EG is equal to, did you crank that out for me? Just
minus 24.
Minus 24. I'm going to put a plus 24. And I'm going to swear you all to secrecy. No one thinks that I'm not better than that at guessing arrowheads. And you better not tell them. That means this EG arrowhead was changed. That means this EG arrowhead was changed. And that means the answer was changed. That means not that it goes to the right. Doesn't mean that it goes to the left. It doesn't mean anything except the arrowhead is now on the proper end of the stick. Since the arrowhead is shown compression, pushing, it is compression. Yes, sir.
So when you draw the arrows as if they're going outwards,
It was a,
that it's intention, right?
that is what I assumed. That was a poor assumption.
The way I usually do these, I'll assume
I don't
it's
care.
intention. No,
See me after class and tell me how you do it. And then if I think the whole rest of the class wants to know that new, fantastic,
it really is fantastic.
see me after class. I know you just can't hardly restrain yourself, but you are going to have to. All right. Now then, next, I've assumed this is intention. Now, if you want to know the truth of the matter, if you kind of look, I know usually the top of the truss is in compression, so that was probably a bad guess to begin with. This one here, I'm going to solve for FG. I'm going to follow the two people I don't like until they meet at a point. They never meet at a point. That means that it's okay to drop back to one of your easier equations. Some force is horizontal or vertical. Can't sum forces horizontal just yet because you don't even know this guy. I don't even recommend it because he may be wrong. But if you'll sum forces vertical, then these two people you don't like will drop out of your equation. So I would say to solve for FG, you should sum forces in the vertical direction is equal to 0. Now, do I think it's going the proper way? Yeah, I think it probably is because there's 12 down and only 9 up. And so this guy is going to have to help in the upward direction. The arrowhead's probably guessed correctly. Sum forces vertical is equal to plus 9 minus 12 plus FG. And as soon as you look at that, you say, wait, wait, wait. All of FG doesn't point vertically, only a piece of it does. And the amount that points up is 1.8 out of 3. And if you don't get that, you're getting behinder and behinder. And therefore, FG is equal to, and you know how to use a calculator. Finally, I'm going to solve for the force in member FH. I like FH. I hate FG and I hate EG. I follow them until they meet at a point. They meet at point G. I know that because they both have G in their name. Now you say, well, but that's outside the free body. That piece of steel shouldn't rotate about any point. B, D, C, G, P, M, Q. It's not supposed to roll about any point, so it's perfectly acceptable for you to sum moments about a point outside the free body. To solve for FH, I would sum moments about G equals 0 is equal to. I see a 12. His moment arm is 2.4. He tends to roll. Were he to get away from us? Positive. I see a 9. No sign. I see a moment arm. 1, 2, 3 times 2.4. Were he to get away from me, he rolls negative. Then I see FH. He has a moment arm about G of 1.8 meters. And were he to get away from me, he would roll positive. There's 1, 2, 3. These two go through the point. And so that ought to solve for FH. If it comes out a plus, leave the arrowhead alone and call it tension because you guessed tension. If it comes out minus, change the arrowhead and change all your equations. That's my suggestion. If you want to just stick a little old minus sign on there and hope I see it while I'm grading it, that's okay, but it's not probably what you ought to really do. And when you get out, it's probably not what you ought to do either. We get everything else the same way. Other things that we could get, not by method of sections, we could go to this joint and get a couple of answers by the method of joints. You would find that Baker dog is what? Don't everybody answer at once. That's so confusing. Mr. Garza. Well, you know, I saw you text messaging her. Hey, honey, I could even see the keystrokes. What are we going to do tonight? Wow, all right. Mr. Garza, that's a special piece of steel right there. Why is it special? Hint, hint. Pair of parallel forces coming into a joint. Hint, hint. Somebody else coming in. Hint, hint. Zero force member. Hint, hint. Zero force member. Very good. It's a zero force member. You want to solve for it? Certainly okay with me. When you draw the free body of joint B, it'll become more obvious. Now that you know, have got this one drawn here, you could move on to joint A, 2 new unknowns. Then you could move on to joint D, 2 new unknowns, but the chances of getting all the way over to EG without making a mistake are very small and very time consuming. Baker dog, here's the free body for the joint B. Here is the force in member AB. Here is the 9. And here is the force in Baker dog. The rule says if you have two people coming in collinear, anybody else coming in at an angle must be 0. Now that's the rule. But then just looking at it, sum of the forces in the horizontal direction reads, sum of the forces horizontal is equal to 0 is equal to plus Baker dog minus, that's it. And so BD is 0. Does that make sense? Okay.
Yeah, so AB is not used.
AB is not 0 because there's a force coming in. Anytime you have a force applied to the joint, all bets are off. Yes, sir.
Why is there not a horizontal reaction at B since it's a joint?
There's the potential for a horizontal force at B. In this case, since all the forces are vertical, all the applied forces, B horizontal is potentially there, but it is 0. You would have found that out when you do a free body of the whole structure to begin with. All right, now we get one that's really the purpose for today, slightly more complex. I have a truss. I'd like to solve for the forces in member DF, EF, and EG. Hence the free body shown. When it gets out of, when you can't see what I'm writing anymore, holler at me and I'll back off. I'm going to have to guess. Now, see here. Let's use your fantastic rule that you're just dying to tell us. Don't tell us the rule because I don't think it's going to work. Is DF tension or compression? Dog, fox. Yes, sir. This one right here on the top of the truss.
I'll just assume it's tension.
What was this assume stuff? I thought you had a law, a rule.
Well, I know you don't want to hear about it. I'll just say tension.
Okay. Well, okay. And you may indeed be right, but I really worry about it a little bit. I really do.
I'll tell you.
No, I don't want you to tell me. Due to symmetry, I can tell you the reaction is 2.5 P. We'll have to go ask the boss how much load he really wants. He just told us in terms of the symbol P. He thinks it's in tension, so I'm going to show it in tension, and I'm going to give it a name, DF. This one, I don't know. See, now I don't know. There's 2.5 up and 2 down, so this guy's winning. We need some downward help. But if this guy really is already helping downward, this one may be having to pull up to balance it. I don't know. I can't outguess this. I'm not going to take that chance. I'm going to put it somewhere, and if I get a minus sign, I'm going to change it. And then the bottom one, the bottom of trusses are normally in tension, but normally they don't have these little ends sticking out past the reactions either. So I can't tell you. I'm going to guess them all tension. PG. I will get the right answer before it's over with. That's for sure. I will put slopes on any members that are cut and have slopes to them. Good morning. DF has a slope 7.5 by 18. So this is 36. So this goes over 18. It goes up 7.5. So this slope here is 7.5 by 18. And if someone would square root that for me. Thank you, 19.5. And then this one, I can get the dimensions right on the triangle. I can't hardly put them there. This one goes over 6, and it goes up 7.5. And therefore, the hypotenuse is 9.6. Any more accuracy than that? 9.60. All right, that's fine. I just want to make sure that we usually round things out to 3 decimals. All right. Now then, I am ready to solve for the force in EG. Who do I like? Dopkin. Who do I like? I like EG. That's right. Look at this. See there? I like EG. Winfield. Who do I hate? I do indeed. Because they're stopping me from getting a quick and easy answer. All I got to do is follow them until they meet at a point and some moments about that point. You can even tell which one it is because they both have the letter F in their name, and so that is a point we should some moments about. Equation 11, I don't know how many I've used up to this point. Using free body number 6. Using free body number 6. I always tell the guy what I'm doing so he can follow my work. That way if I make a little mistake, he'll beat me slightly. If I don't tell him what I'm doing, he'll just look in the bottom and look in the box. And if the number is wrong, I get no credit at all. Equation 11 says sum of the moments about point F is equal to 0 is equal to. First, I see a load P. Thank you. And it has a moment arm of 18 feet. Next, I see, and it is a plus. If you don't see any of these signs, you need to holler or you need to come see me afterwards. Next, I see a 2.5 P load, and it has a moment arm of 12 feet, and it is a minus tendency to roll. And then I see a load P, and it is 6 feet away, and it is a positive tendency to roll. And then I see EG, and he is 7.5 feet away. I mean, there's not a lot to this. And he is a positive tendency to roll as guessed. And then I solve for EG and I write down the number. If it's tension, I leave it alone. If it turns out a minus sign, that means this arrowhead was wrong and it should be shown compression. Next, I'd like to solve for, and I think I got another free body for that because that one's getting kind of busy. Next, I'd like to solve for the force in member DF. There was DF. There was EF. And here was EG. To solve for DF, I like DF. Who do I hate? I hate EF and EG. They both have the letter E in their name, which indicates they'll be meeting at point E. That's where I'll sum moments. To solve for EF, sum moments about E. This is free body number 6. It's the same one we had a minute ago. Using free body number 6, my 12, 13, 14, this is probably about 15 if I completely solve that other set of forces. Oh no, that's wrong. That's what we're doing now. This is equation 12. Some moments about E is equal to 0 is equal to. All right, EG goes through there, so I don't have to worry about him. EF goes through here. Well, that's good. That's why I did this. The load P goes through there. Here's the reaction of 2.5 P. 2.5 P times his moment arm, 6 feet. His tendency to roll is a negative tendency to roll. And we have a force P. He's 12 feet away. His tendency to roll is minus. And next we have DF. Positive, it certainly is, thank you. Yeah, several people just died. Okay, and next we have DF. But he's got a moment arm that I wouldn't wish on my worst enemy. Can you solve for it? Certainly. In math, you learn how to solve for the shortest distance between a point and a line. And if you remember how to do that, more power to you. So what I'm going to do is, rather than find easy DFs times his hard moment arm, I'm going to go ahead and make DF hard. By that I mean I'm going to break it up into its components and throw away the original force. So I mean that's hard. I mean it takes work to get the components, but now then those components have nice, easy moment arms. Okay? This is DF vertical. And this is DF horizontal. And DF horizontal is equal to DF. Well, pretty close. I mean, at least it's a piece of DF. And looking back at our slopes on DF, 7.5 by 18. 7.5 by 18 by 19.5. That says that if you would multiply DF times the horizontal piece of the slope triangle, then you'll get the horizontal component. That's 18 out of 19.5. And for the vertical component, to tell you the truth, I don't care. Green, why not? Green here today? Well, I'll take either one. Guy green, as opposed to lady green. Good point. I forgot it. Because it goes through the point E. Absolutely correct. That's the point I'm summing moments about, so I'm not going to bother solving for it. And so all I got to do is multiply DF dollar times 18 over 19.5 to get his component. Then I have to have a moment arm to go with the force. And the moment arm is going to be 1, 2, 3. It's a third of 7.5 feet. No, it's up there 2/3, isn't it? 2/3 of 7.5 feet. 2/3 of 7.5 feet. And his tendency to roll for the component is negative. How do you shut this thing off? Take the battery out. One equation, one unknown, bingo. We have the answer for DF. Now there's a big tendency for students to say, well, okay, now that I've got this thing, do I have to now turn it into the force? This is the force. All work talking about turning things into components was done already with this number here. So when you put this number back in the equation, you get the final answer for the force in dF. Next, I'd like to solve for the force in EF. That was dF. This is EF. And this is E somebody. I would put the slope on this member dF, but with any luck at all, I'm not going to need to even look at him, and so I'm not going to bother. EF's probably going to need that slope. That slope was previously determined as 6, 7.5, and 9.6. Who do I like? EF. Who do I hate? DF and EG. Well, that's interesting. They don't have a common letter in their names, but maybe they still meet somewhere, but it's just not right off the bat. So I'll follow the guy I don't like, and I follow the guy I don't like, and they do meet at a point. They meet at point A. They don't have A in their name, but they still meet there. And therefore, to solve for the force in member EF, some moments about A equals 0. Now, if you're bored to tears, I love it. That means I shouldn't be doing all this anyway. But if you're not sure what's going on, when we start trying to find out statically indeterminate forces in trusses and you need to find these force members, you're at a serious disadvantage. So, this is still free body number 6. It's just redrawn. This is equation number 13. Some moments about A is equal to 0 is equal to. The reaction is still there at a 2.5 P. Boss still has to tell us that number before we're going to get any answers. Times his moment arm. He is a positive tendency to roll. Next, I see a load P, 12 feet away. He's a negative tendency to roll. DF and EG both go through point A, so I'm okay on that score. And now I need EF times GFM, a goofy moment arm. And the moment arm comes down here, and that's a positive tendency to roll. So if you don't mind, I'm going to replace that by the two components for EF. One of them goes to the right, that's EF horizontal, and one of them goes up, that's EF vertical. I'm not going to bother finding EF horizontal because it goes through point A. EF vertical does not, and it is equal to EF. Wait. Not all of EF vertical is equal to EF. Only a piece of EF vertical is equal to EF. Clapton, what number goes right there? Let me give you a hint.
You want the vertical part?
I want the vertical part.
7.5 and 9.6.
Very good. Not the fact you got the answer right, but that you could read the writing. All right, so right here we put 7.5 out of 9.6. And right here we replace EF dollar mark with EF dollar mark times 7.5 over 9.6. And then, of course, we don't have to have a goofy moment arm. We have a nice easy moment arm for that vertical component, and it is 12 feet. And at that point, I lose all interest in the problem. Because EF dollar mark, all I got to do is get a calculator or a friend with a calculator, and I'm done. Questions? All right, let's try this one. I'd like to find the force in member DF, EF, and EG. You'll notice I avoided the reactions because now I don't have to solve for the reactions. The forces in those members do not depend on them. We'll write down what we're going to do only this time. This is the force in member DF. I have no idea which way they go. This is EF, and this is the force in member EG. Almost assuredly, since these loads are pressing down on the structure, EG is in compression. Without a doubt, that's going to prove to be the wrong direction. The slope of this member, the slope of that member is, you got to do a little thinking now. This is 3 feet down to here. So this is 1 foot down to there. And remember, EG is half of that downward movement. So EG drops a half a foot. And it has a horizontal run of 4 feet. EF, on the other hand, drops down 3 feet plus a half a foot. I mean, you do have to be careful, and you got to be able to add. So it has a vertical of 3.5, has a drop of 3.5, and it also has a run of 4 feet, a horizontal slope distance, 4 feet. Anybody happen to get me this one already? 4.03, thank you. Anybody happen to get me this one? Is anybody going to get me that one? Would someone please get me that one? Never mind. Carol? Okay. 5.31. On your next quiz, put plus 1 point. Just remind me why. A little short note. Was the only person awake on 9908 or had a calculator. All right. So now that I'm ready to solve for the force in member DF, if DF is who I'm looking for, to solve for the force in DF, I would sum moments. Straub, what point would I sum moments about if this is the guy I'm looking for? That's correct. You'd sum moments about E is equal to 0. Summing moments about point E would drop out the two unknowns that are giving you a hard time. You have to be a little careful with your moment arms. Make sure you get your moment arms right. For instance, DF will have a moment arm of 3.5 feet, and these guys, of course, will be easy. Now solving for EF. No, I don't want to solve for EF because well, you'll see in a minute. I want to solve for EG. Since I want to solve for EG, I dislike DF and EF, so I will sum moments about point F. To solve for EG, some moments about F. Equation would read, I don't know which equation number it is, some moments about how do you turn these things off? That doesn't do it. That'll do it. Some moments about F is equal to 0 is equal to. Well, that's all I care about because I know how to sum moments about F. I would have to break EG to get him into components. I'll need an EG horizontal, and I'll need an EG vertical. And actually, they'll both have moment arms in there. And so I'll get an equation that has EG horizontal and EG vertical both in it. And you say, well, now then you got two unknowns in one equation. And that's hard. Well, that is true. If you would find this moment arm, this shortest distance between those two, that line and that point, you'll get EG directly. But that would be my equation 1. I'd still stick with it. And my equation 2 would say that EF vertical is to 3.5 as EF horizontal is to 4. So my first equation would have EF vertical in it, and it would have EF horizontal in it, and I would solve for EF vertical, and I'd drop it in right there, and I'd get EF horizontal only. Then knowing EF horizontal only, I'd say is equal to EF time divided by 5.31, and I'd get an answer for EF. Now then, I'm going to solve for the force in EG. We already did EG.
Well, no, when you started solving for EF.
Oh, I did? Oh, that's right. I said I didn't want to do that one. Right. Well, the reason is because I got a free body for that one, but it needs to be on the other side of the page. Good point. Thank you. So we are now solving for some moments about F. I don't see what else.
You were solving for EG, and then you went into halfway there you switched.
Okay, so all of these are wrong. What are we really solving for on this one? EG, thank you. So we were going to solve for this one, so we saw moments about F, and I didn't go back and fix that. Thank you. All right. We can solve for EG. It's not that bad a deal. There's EG. There again is EF. Yeah, I know. Hard work. That's why they pay you the big bucks. Now then, if I'm going to solve for EG, that'd be some in moment. I'm solving for EF. Good. To solve for EF. That's why I put this off till now. This is the strangest one of the bunch. To solve for EF, I do not like DF. Let me follow him. And I do not like EG. Let me follow him. Oh, my Lord. And that's the point I'm going to sum moments about. Point L for Lowry. Now, you don't have to. You can take your chances. You now know this guy, and you now know this guy. And so you could sum forces vertical and solve for this. And, you know, if you got this right, then you'll be okay. But from a purist point of view, if you want him and you don't want them, follow them until they meet at a point. Here's where it meets at a point. This member ramps up a half. This member, one member right here, ramps up a half every time he moves 4 feet to the left. He goes up a half a foot. And past this point, we have 6 of these to go up. I'm sorry, 3 feet. So we got 6 half a foots to go up. And so I'll tell you now, we're going to end up out from here. 1, 2, 3, 4, 5. We're going to end up 4 feet over to the left of this point right here. Similar triangles works out nicely too. Here's a similar triangle that says 4 is to a half. Four is to a half as x let's only go this far, as x is to 3. And that'll take us to here, as x is to 3. So x is equal to 3 times 4 is 12. Boy, that don't look right. Is it right? So x is equal to 12 divided by 0.5. Oh, that's in feet, isn't it? That's not panels. Thank you. So that is 24 feet from point B. This triangle is similar to this triangle. So we're going to go out here to the left, 24 feet to the left of B. That's 4 feet. So let me just show you, these already have dimensions. This is 20 feet. Now let's see if we were right before. I told you we would be moving over. Darn, I don't remember if that's one of the numbers I counted or not. 1, 2, 3, 4. How many did I say? I said we move over 6. So that's 1, 2, 3, 4, 5, 6 at 4, 6 is 12, 24 feet from here. That's correct. Both of them give you the same answer. So now then you know where you're going to sum moments about. You're going to sum moments about L equals 0 is equal to. EF still has to be broken up into components. Ooh, I just noticed something pretty nifty. You are welcome to break up. I don't know how in the world I'm going to do this because I didn't leave a lot of room. You are welcome to break up any force into its 2 components anywhere along its line of action. Therefore, at E, you can show me EF vertical and EF horizontal. But EF vertical and EF horizontal will have moment arms. If you'll go ahead and move E to this point, that's point F, and splat it into 2 components at point F, perfectly legal to put it here or anywhere else along its line of action. This would be EF horizontal. This would be EF vertical. This guy here now would have no moment arm. And so it also would drop out of your equation. A sneaky but nifty move. and then you'd solve for EF vertical, be the only unknown left. All right, so now hopefully that's what they taught you in 221, and hopefully you are now you remember what you were taught and you're familiar with it, and you can find these forces in truss members. So let's move on to bending, something you already supposed to know how to do. Right quick, let me try and show you why you need to be able to draw shear and bending moment diagrams. If you have a load on a structure, that's called the load diagram. Beneath that diagram are several more diagrams which can be found by simply integrating the load diagram. You can do it mathematically, you can do it using either singularity functions, or you can do it, I don't think you had singularity functions. Yeah, you have, this is 345. You can do it singularity functions, or you can do it by ranges. In other words, this would be AB would have a moment equation and BC would have a moment equation, and you could do it in ranges. Singularity functions is pretty nice. Doing it in ranges, you have to tie things together at this point. One integral of that would give you the shear diagram. My guess is you learned how to draw a shear moment diagram graphically. First you solve for the reactions. I'll leave that for you. Shear diagram was obtained by starting on the left-hand end, and as you go across any areas, the area that you cross tells you the change in value on the next diagram. That's what an integral is. So the shear diagram jumps up 150 because you started at 0. As you go from the right of A to the left of B, you can't go to the right of B because something new is going to happen. You can't even go to the middle of B because a half of something new has happened. As you go from the right of A to the left of B, no loads say go up and down, and so you didn't go up and down any. As you go across the 200 kilonewton force, it drives the next diagram down 200 lower than it used to be. That puts you at 50 below the line. We don't usually mark it as a minus since it's below the line. As you go from the right of B to the left of C, no loads say go up, but also none say go down, so you just drag your pencil across the page. And as you go across that 50 kilonewton reaction, drives the diagram up to 0, and these diagrams are supposed to close on 0. Now, the next diagram is the next integral. If you integrate the shear diagram one time, you get a moment diagram. The truth is, there's no difference. If you called that the load diagram, and it could be, I could load a beam like this, then the next load you'd get would be one integral away, would be the shear diagram. This would be area 1, and this would be area 2. It's usually a good idea to just go ahead and calculate these areas before you get started drawing. Area 1 is equal to base times height, because it's a rectangle. It's equal to 150 kilonewtons tall. It has a base of 2 meters, so the area is a positive. Now, in this diagram, the little arrows tell you which way the next diagram moves. On these, you just have to use the areas. If you work from left to right, the areas agree with what most people use for a positive sign convention. Johnson? I think your buddy, no, that's okay. I thought your buddy next to you there had died, and I just wanted you to call his mom. Are you all right? Okay, that's okay. As you go from A to B, you cross an area A1. Let me see, I didn't finish this. I got fixated on picking on somebody. Area 2 is equal to a negative area. It's a base times height, and the height is negative. That's equal to a minus 50 times 6 meters. So we have an area of 300, but it's a minus. That's good, because plus 300 balances a minus 300. And it ought to. So as you go from A to B, you cross area 1. And it drives the curve up by an amount 300. So we're now 300 kilonewton meters above the axis. Straight horizontal lines. That's an x to the 0 power. What does an x to the 0 power integrate into? X to the 1. So it's a straight sloping line. As you go from B to C, you cross a negative 300 kilonewton meters, which drives the diagram down to 0. The reason you draw shear moment diagrams, of course, is to get the biggest moment in the beam to make sure it's not overstressed. A second reason that you draw a shear moment diagram is because it will tell you how the beam deflects, and we'll be able to calculate that numerically in a few days. Now, what I'm going to do now is just kind of draw them, because rather than sketch them graphically, it's easier to get numbers a lot of times just by doing mathematical work. But I can call that area 3, and area 3 is equal to, it's a triangle, so it's 1/2 base height. It is a positive, and so that's equal to 1/2 the base is 2, and the height is 300, so half of 2 and 300, that's okay, that's 300. And the base is meters, and the height is kilonewton meters. And the truth is, this next diagram we get is the slope of the beam. And actually we'll derive it, but once you integrate the moment diagram, it gets divided by EI. That's how come the units don't look like a slope. This ought to be radians. So once you divide it by EI, these units will drop out, and that 300 won't have any units to it. And this area here, this area is 1/2 the base times the height. That's area 4. So area 4 is equal to 1/2 the base is 6 meters. The height is 300 kilonewtons. And therefore, half of 6 is 3. 3 of 3, that's positive 900. As you can see, something fishy here. All of a sudden, these areas do not add up to 0. Both of these areas are positive. Well, the reason for that is the original beam is got this kind of a look to it once you put the load on it. It's not symmetric, but it starts off with a large negative slope. And I don't know what that number is, although I could find it, and you will be able to too. So if you drew the slope diagram starting at 0, you would then add area 3, or you'd go up to 300. And then as you go across area 4, you'd add another 900. That puts you 1,200 above the line. But that's slope. Now, this curve is an x to the 1 power, so this curve here will be an x to the 2 power. And a 0 value here gives you a 0 slope. And a large value gives you a large slope, so it actually looks like this, and then it looks like this. The only problem is the whole thing's in the wrong place, because due to the way the beam is loaded, the left-hand end of the beam does not start at 0 slope. So I would have to come down here some number, and I don't know what that number is. We will later on, but this is just positioned wrong because of the boundary conditions. And then the last one is the deflection diagram. I do know the deflection on the left end of the beam is 0 because it's supported there. And I do know that the deflection there is 0. Now then I got these goofy areas here to calculate, and I don't even know where that 0 point is, and so I'm pretty much out of business. I can sketch it for you, but I could have sketched you the deflection diagram before we even started. I mean, the beam bends down a lot. It does not have 0 slope under the load. It actually has 0 slope a little to the right of the load, but not in the middle either. And there's the deflection diagram. This negative area is pushing the diagram down. This point of 0 is actually should be right there. And then this positive area pushes it back up to 0. That's the mathematics behind it. Like I say, there's a lot easier. There's no easier way to get a shear diagram. There's no easier way to get a moment diagram. There's a lot of better ways to get these, but here's where they go. This is where they reside. Now, when we started that, I told you, let me show you why it's important you be able to solve for this deflection or any other deflection on the beam. I have no idea what page number we're on. Here is a beam that is supported in the middle of the river. And here's the load you just saw on the beam. What they found was that the moments are greatly reduced and the safety is greatly increased if you'll add additional supports and make the structure statically indeterminate. And I will show you how the beam deflects. It deflects kind of like that. And here is the load, 200 kilonewtons. And here are the dimensions, 2 meters, a new support at the 2 meter mark, and a support at the 4 meter mark. You can't solve that problem by statics. Your 221 prof was derelict in his duty because now then you can't solve half the structures in the world. So what you'll do is you will come in here and lie about the structure, and you will remove what is called a redundant. Any of those could be removed and called the redundant. Normally we remove the middle one, and we show you the deflected shape just like we did before, and you say if the boss ever sees this, he'll have a fit. That will be called the deflection due to at point 1, depends on how many unknowns you remove, due to the real loads. Then you will come back in with a hydraulic jack, and you will put a magic number on the beam just right, just perfect to get rid of that unwanted deflection And the answer will be equal to the answers you got from this case plus the answers you got from that case. This number right here will be called the deflection at point number 1. Gee, I already call that due to the real loads. They really call it delta 1 0. And this is delta at point 1 here. A better name than that. I guess you get the idea by now that the naming is pretty much your business. This is the delta at B due to the redundant R sub B. And until you can solve for these deflections, you can't solve for this unknown force. Until you solve for that unknown force, you can't solve for these reactions. And until you can solve for all these reactions, you can't draw me a shear and moment diagram. And until you can draw me a shear and moment diagram, you can't design the beam. And until you can design the beam, none of that for you. All right, let's try another one. Well, let's don't. I'll tell you what I'm going to do instead. I'm going to write equations for the case we had. I'm going to write equations because I'll admit to you now that we're getting ready to integrate these rascals. To get these answers. Write equations for a moment for the case on page 36. And here that case is right there. The way you write the equations for that beam is you cut the beam in the region of interest. Here is that beam. Here it has been cut. Here is the reaction, 150 kilonewtons. Here's the name of this, and B is over here where it hasn't yet been cut. Generally speaking, there is an unknown axial force, might be called P at X. Let's call this dimension X. There is in general a shear. The shear at X. Is he okay? Oh, you just dropped your book? Sometimes that's the sound of the student hitting the ground. And here is a bending moment, M at point X. Two of them, wow. Now then, all you got to do is solve for the unknowns and admit that they are a function of X. Some forces in the horizontal direction is equal to 0 is equal to minus P sub X. Well, there aren't any other forces on there, and therefore there's no axial loads in this thing, so we probably won't even solve for P sub X. Sum of the forces in the vertical direction is equal to 0 is equal to plus 150 minus the shear at any point X, and that gives you an equation for the shear at any point X. This is good for X, 0 less than X, less than 2 meters. Everybody has to know what your equations are good for. So probably ought to put that up here. 0 less than X, less than 2. That's what we're doing now. Answer for shear of X, it is not a function of X. It is 150 kilonewtons in the direction shown. And finally, sum of the moments about the cut face. Ooh, that works nice. Sum of the moments about the cut face. You do not have to sum moments about the cut face. You can sum moments about A if you would rather, but if you sum moments about A, don't forget to include V sub x and his moment arm. Whereas if you sum moments about the cut face, then that shear will drop out. Is equal to 0 is equal to minus 150 kilonewtons times his moment arm, x, plus m sub x. And therefore an equation for m sub x, good only for the range 0 to 2, is equal to a positive, means the arrowhead was guessed properly, means that compression is on the top of the beam and tension is on the bottom of the beam, 150 x kilonewton meters. Next, I want to know the equations. This is what it says, 0 to 2. Now I want to know the answer for 2 less than x less than 8. Let me redraw the structure. It's getting hard to see. Here's the structure. Here's the load. It was 200. This was 150. This is, it goes on out here to this other reaction. There's the beam. That's 2 meters. This is what I'm calling X. Guess I didn't really redraw the beam. I drew enough of it to get the job done. Here's the shear. The downward load's beating up on the upward load. To tell you the truth, we usually show the shear in the positive direction. That's down on the right, and we show it even if it's wrong. We pretend like we don't know and we guessed it down. That way, if it comes out a minus, we know the shear is really negative in that region. That's V sub x. And here is M sub x. It is also shown positive, even if we know it's wrong. In this case, I don't know if it's going to be right or wrong. I don't know. The equation says sum of the forces in the vertical direction is equal to 0, is equal to plus 150 minus 200 minus V sub x. And believe it or not, we don't change the arrowhead when we're working with this stuff because we want the minus sign to indicate the shear is wrongly drawn, but it's also a negative shear in that region, minus 50. And then we sum moments about the cut face is equal to 0 is equal to, there's 150 times his moment arm is x, and then there's, that's a minus, and then there's a 200, and his moment arm is x minus 2, and he is a positive, and then we have m sub x, and he's a positive. Therefore, the equation for m sub x is equal to 150x minus 200x, is that right? Goes on the other side, 200x goes on the other side, 200x. 200 times 2 is 400, minus on the other side is plus 400. And the answer is minus 50x, unless I got a sign mistake in there. I'm running out of time. But you know that, don't you? That's the equation you need. That's the equation you will be integrating. It'll only be integrated from 2 to 8. Stick around if you have any questions. If you came to class late, I did take roll.
I didn't get my quiz back. It wasn't in the
Look and see if it's maybe next to it. Every now and then somebody takes them out, and when they put them back in, they put them in a wrong slot. Name. How do we still have... Okay. Well, I know why. I haven't reprinted this out yet. All right. So this is, I don't know who this is because there's nobody there now. Hang on if you got time and I'll listen to your spiel. Seat number? 74. 74, gotcha.
Are you switching anybody?
No, I'm just trying to straighten out who actually ended up coming, but just came in late. Seat number
77.
77. 66. Now your method is?
Well, I was just saying, you assume everything is intention.
I did that time, but not always. Sometimes I do a better job of guessing than that.
Well, I noticed that you'll change them after you realize that it's the wrong direction.
I always want to because the reason is, you know the reason I told you. You remember the reason? No? Okay. The right answer is minus 200. And that tells everybody on Earth that arrowhead is compressive instead of tensile. But the guy designing the thing who doesn't notice that little bitty minus sign and designs that member not for buckling and it drops on their heads, they'll sue him and they'll sue you too. So I just go change them and make all the arrowheads proper.
Well, the way I figure I would do it is I won't change them as I'm doing the problem. I'll do the entire problem.
That's
assume
okay.
intention, and at the very end, or where I have pluses and minuses, instead of plus and minus, I'll say C or T for tension.
Well, that's okay. I mean, many people do it that way, so I have no complaints about that.
Okay.
You know, you won't either. See, I was
That way
thinking...
you're consistent throughout the entire problem.
Yeah, that's true. I was thinking you need to be careful when you move from this free body to that free body, but you're going to have it wrong on both of them, and you're not going to change either one of them, so you'll be okay.
Yeah, I'll be consistent.
I buy that.
Otherwise,
Yes, sir.
When is homework late if you don't turn it in during class?
Yeah, beginning of class.
Well, I had it done, I just left it at home, so that's why I was late. But I was making sure I made the right decision not going to class, or going in late.
Okay.
I've got a question on some of the moments about A in this
All right. Some of the moments about A.
Because we're getting the, it's like, they were saying that we need to square it up, but I was wondering why you'd square
No,
it up.
you can't square it up. That guy has to be shown as a force in this direction.
Right, because that's the perpendicular moment.
That's correct. And not only that, it's going to have if it's at right angles to this member, then it's okay. Its moment arm is right there.
Yeah, because I was working on it with them, and they were saying that like splitting it up into the B vertical and B horizontal component. But it looked to me like if you do that, then you lose like this axial part. Right?
Well, no, you don't do that. In other words,
Yeah.
let's just say that this is really what you're going to call the reaction at B. And I don't know, are you going to hand this in for anything, or is it just
No.
notes?
Like I did it this
It's
way.
just junk. Okay.
I was just-
So
I
let's
was
just
just
say
clear
that this was a 3x4 slope.
Yeah, that's.
And
that's
let's
what it is.
assume that this guy right here is a 5x6 slope.
Yeah.
All right, well, then his moment arm is not just this nice, easy number.
Okay.
Okay? And therefore, what you need to do is you need to show the entire structure, and you need to show RB vertical as RB multiplied. Man, I hate that 5/6 because I don't know what the hypotenuse is. Let's make it a 3/4. No, that's no good because you already got a 3/4/5. Let's say that it is a 5x12x13. Okay, that's a triangle that's kind of standard. Then for the vertical part, you'd put RB times 12/13. And right here, you would put R sub B times 5/13.
Okay.
You have no choice unless you want to find this horrible moment arm.
Okay.
Okay? And then when you sum moments about this point, you will have these two guys show up in your unknowns.
Okay.
You would then say that RB vertical is to 12 as RB horizontal is to 5. You would solve for RB vertical and drop it in right here. Okay. Getting rid of that unknown in your equations, and then you solve for RB.
Okay. All right, thank you.
So what you did, I think, was the right move.
Okay. Cool, thank you.
Okay.